This video is going to be looking at topic 3B, rates of reaction, for the Edexcel IGCSE single science course. So we're only going to be looking at the single science outcomes here. We're going to be describing some experiments in order to change the factors that affect the rate of a reaction. We're going to be able to describe the effects of these changes, as well as explaining what a catalyst is and the practical that we can use, specifically looking at changing the surface area. So we're going to start off with what actually is a rate of reaction. Well, the rate of a reaction is defined as the change in concentration or the amount of either your reactant or your product per unit time. Now that's very important that we're talking about how much product is being formed or how much reactant is being used in a specific time frame. So we might look at over a course of 10 minutes or 5 minutes or even 1 minute. And we can determine a value for the rate using this equation at the bottom here. So we have our change in either our concentration, our volume, or our mass, and we divide it by our time. So let's have a look at the experiment for this particular topic. So the experiment is between marble chips, otherwise known as calcium carbonate, that's its proper chemical name, and reacting that with hydrochloric acid. Now in this reaction we're going to form carbon dioxide gas. We do also form the salt and the water, but that actually doesn't help us in any way. What we really want to focus on is we want to focus on our carbon dioxide gas. So you can see in the diagram how we set this up. We have our conical flask that contains our acid and our marble chips, and we have a very specific mass of marble chips. So we've pre-weighed that and we know how much that we are using. We also put some cotton wool into the top of the flask, and that is to stop any acid from escaping. Now, a very common mistake that people make in exam questions for this is to say that the cotton wool is there to stop the gas escaping. Now, that is not correct. We do actually want the gas to escape. As you can see on the balance and the second part of the reaction, we are getting a negative number here. This is meaning that mass is lost in this experiment, and that mass that is lost comes from the gas. So we want the carbon dioxide gas to escape from the flask through the cotton wool, but it stops any acid escaping. We do not want the acid or any of our marble chips being removed from the conical flask, because then it will make us look as though we are making more carbon dioxide than we are. So the entire point of this is to measure the mass that is lost. And what we would most likely do is we would take regular measurements. And that's probably maybe every minute for about maybe 10 minutes in total. It depends on how much of the hydrochloric acid and the calcium carbonate that you use. But what's important is that we take a note of the mass every minute or every 30 seconds for a specific amount of time. Now, when we do get these results, then we can plot a volume of the carbon dioxide being released against the time. So this is going to be our volume of CO2 that is being formed, and this is going to be our time. So you can see that we start off at 0 at the beginning because we don't have any carbon dioxide, and we curve up, eventually leveling off. And where it levels off, this means that the reaction has stopped. Now the reaction will stop probably because we've used up all of our reactants, and it depends on which one is going to be used up first. That can vary. Sometimes it can be the acid, sometimes it can be the marble chips. It just depends on which one you used in excess. But you're not going to be asked about that. What you may be asked is to explain what the graph shows. And the graph is there to tell us about the rate of the reaction. And it is this bullet point here. The steeper the slope of the line, or the higher the gradient, the faster the reaction. So we can see at the beginning here the line is particularly steep. So this is going to be a fast reaction at the beginning. As we get further up the time and we get further up the curve, you can see that the curve starts to level off. So it becomes a slower reaction until eventually the reaction stops. And when it stops, we start to see this completely horizontal line. So we can actually interpret the rate of a reaction just by looking at the shape of the graph. Now we can also calculate the average rate, and we can look to see for any time interval. So you would have a certain amount of data that would tell you how much mass is being lost or what volume is being produced. It just depends on the particular question. And you can work out for the first minute, the second minute, or the first 2 minutes, or any time frame, what the rate of that reaction is. And all you do is you look at how much mass is lost, and you divide that by the time frame that it is lost in. So for example, the average rate of reaction in the first minute, we lose a mass of 0.47 grams, and that happens in a time frame of 1 minute. So 0.47 divided by 1 is of course 0.47, and our unit here is grams per minute. We can then do the same thing for the second minute, and we end up with an answer of 0.2. Notice that the reaction is fast at the start, and then it is slower as the reaction proceeds. And we can also find the average over the first 2 minutes if we wanted to do that. So the rate of our reaction is going to be the fastest at the start, so we will see a lovely steep graph. It will then slow down as we start to use up the reactants, because there are not enough of the reactants left to react. So the graph becomes less steep, and eventually, once all of the reactants are used up, the graph becomes level. This is going to be the same for any chemical reaction that you're going to come across in IGCSE with regards to rates. It will always be fast at the start, a little bit slower, eventually leveling off when the reaction stops. So that's our practical experiment, and this is all about how we are measuring the rate of reaction. Now what we can look at now is, well, how can we change that reaction? How can I make it faster, or how could I make it slower? And the way that we do that is we have to understand something called collision theory. Now, in order for the particles to react, they have to collide. So to collide, if you're not sure what it means to hit each other. So in order for A and B to react, they have to hit one another with a specific amount of energy or at a specific speed, and then once they collide, they will make the product AB. You can see that the two molecules are apart, they then hit each other, and then they become stuck together. So this is our chemical reaction taking place, and we form this product. Okay, and it's very important that we understand that we have to have a specific energy or a specific speed in order for this reaction to happen. And what it is it makes sure that we overcome all of the repulsive forces that are within the atom or the molecule, and we break any bonds that are present. Because a chemical reaction is just a rearrangement of the atoms. So we have to break all of the bonds and then reform them in a different way. So here's a slightly better drawing of how collision theory works. So a successful collision here, again, is between A and B. And you can see that we have two atoms that are going to be bonded together. These two things are going to collide or hit each other, and they have enough energy where they will stick together in this complex just for a second, and then they will split apart, forming our new products, AB and AB. So I'm just going to go through that again. We have the bonds between A and between B breaking, and then we form new bonds between 1A and 1B in order to give us our products. And this is a successful collision. An unsuccessful collision is when A and B are going to hit each other. They do not hit with enough energy. So what happens is they just harmlessly bounce off of each other and they do not form any products. Okay, so we haven't got a chemical reaction happening in this particular collision. Now, when we're discussing rates of reaction, this phrase is one of the most important phrases that you will have to use. If you're explaining a rate of reaction, or you're talking about anything to do with collisions or anything to do with rates, you should be mentioning successful collisions. So there are 4 factors which can affect the speed of a chemical reaction, and we have to be able to describe the effects of all 4 of these. So we've got particle size, concentration, temperature, and catalysts. So let's start off with particle size. For a solid, the chemical reaction can only take place at the surface. So you can see when we've got our big lump here that the red particles are hitting the blue particles, but all of these particles in the centre are not going to be touched. So they are not actually reacting, they are just sitting completely idle because they are hidden in the middle of the solid. If I take that same lump and I put it into smaller pieces, you can see that all the particles that were in the centre, most of them are now available in order to react. And there are still a couple of particles hidden away, but you can see that it is a much smaller amount than what we had in the first reaction. So all of these particles are all hidden as opposed to the much smaller number here. So when we're describing particle size, we should be stating that the smaller the particles of a solid, the larger the surface area. So we're getting more surface for our reaction to happen, therefore the faster the reaction. This is a key sentence that we have to know. When we look at concentration, we're going to be increasing the concentration, and what that does is it gives us more particles in a specific volume. So it's meaning that we're putting more particles into a space. So for example, in the diagram here, you can see that we have got 1, 2, 3, 4, 5, 6, 7, 8 particles all within this box. As soon as I go to a higher concentration, I have almost doubled my particles, and you can see they are more likely to hit each other. If you need to imagine this, think about if you put people into a room. If I put 3 people into a room and ask them to run around, the chances of them hitting each other are very small. If I put 100 people into the same size room, like a classroom, for example, and ask them to run around, they are almost certainly going to hit each other. This is exactly what happens with concentration. So the key phrase that we have to know is this one here, that the higher the concentration, the faster the reaction. When we're looking at temperature, again, this is a factor that will affect the rate, and when we increase the temperature, it causes every single reactant particle to have more energy. The more energy they have, the more likely they are going to collide. If I use my classroom analogy again, if I take 10 people and I put them into a classroom and I say walk around slowly, the chances of them running into each other or hitting or colliding with each other are very small. If I take those same 10 people and put them into a classroom and I ask them to run as fast as they can all around the room, they are almost certainly going to hit each other. This is exactly what we do with our reaction. Because we have more of a higher energy, we're getting collisions that are more successful. So when it's a lower temperature, sometimes they will still collide, like these ones here, but these are at a low energy, so they're not going to react. When we have a higher energy at a higher temperature, we're going to get a higher number of successful collisions. So these have enough energy to react. So the key terms that we have to know are the higher the temperature, the faster the reaction. Pressure is very much the same. The only difference here is that rather than increasing the number of particles, we're decreasing the volume. So we're making it smaller, which causes the particles to collide more. So the higher the pressure, the faster the reaction. Now we're going to move on to talk about a catalyst. So you know what a catalyst is from Key Stage 3. So a catalyst is a substance which speeds up a chemical reaction, but it is not used up in the reaction. That is very important. Because we don't have to actually use them up, we only need to use very small amounts of the catalyst, and we can process lots and lots of reactant particles. Now, we do not need to know how these catalysts work for single science. We just simply need to know that they speed it up and they are not used up. And different reactions will use different types of catalysts. One that you will come across in both chemistry and in biology are biological catalysts that we call enzymes. And enzymes are very special proteins, and these are within our body, and they allow specific chemical reactions that we need in order to live to happen much quicker at lower temperatures. So it's a way to speed up the reactions and allow them to happen. Some other examples are manganese oxide and lead oxide, and these are used to catalyze decomposition of hydrogen peroxide. You don't need to know how that happens, you just simply need to know that they are examples of catalysts. If you were being asked a question on this, it would give you all the information you would need. So let's have a look at a past paper question. So this is going back to the practical that we had at the start, and we've got our apparatus used to study the rate of reaction. So we have our hydrochloric acid, our marble chips, and our cotton wool, and you can see that we're measuring the mass. So we're putting 15 grams of our marble chips into 25 centimetres cubed of the flask, and we are recording the mass, starting the timer and recording it every 30 seconds. And you can see it is because we have this CO2 being given off. So let's look at the question, and we can always come back to the diagram to see if we need any relevant information. So we want to explain what happens to the mass of the flask and its contents as the reaction happens. So there are 2 marks available for this. The first mark is simply to say what happens to the mass. So the mass is going to decrease. Now, it's not enough just to say that for 2 marks. This question specifically says explain, and that requires you to use the term because. So if it's an explain, you should be saying this happens because of this reason. So the mass decreases because carbon dioxide gas is released and it escapes the flask. And that's your second mark. State why the reaction ends, even though some marble chips are remaining in the flask and have not reacted. Well, let's go back to see what we were reacting. Well, we had our marble chips plus we had our hydrochloric acid. If we don't react all of the marble chips, it must be because we have used up all of our hydrochloric acid. So that is the answer. We just simply have to state that all the hydrochloric acid has reacted or been used up. And state how the student would know when the reaction has ended. Well, there are 2 ways in order for us to see this. We're going to use the way that we're explaining in terms of the actual experiment, and the whole point in this experiment is to watch the mass of the flask. So when the experiment has finished, the mass of the flask stops decreasing, or the mass stays the same. You can also say that it stops bubbling or fizzing, But that's not the best answer to give. The best answer is always relating to the mass, because if we go back to the diagram, you can see that we have a balance. So we do want to be referencing that in our answer. So the student knows that the reaction has finished once the mass stops decreasing. So the student then plots her results on a grid. So you can see that we have the loss of mass and the time in minutes, and we want to look at which time the reaction is fastest. Is it the fastest at 1 minute, at 4 minutes, 6 minutes, or 8 minutes? Well, we know as the reaction continues, it's going to get slower, but this particular reaction is asking us to look at the steepness of the graph. So if we look at 1 minute, which is going to be here, versus 4 minutes, versus 6 minutes, versus 8. Of course, you would draw these with a ruler. We can see that at 1, the graph is very, very steep, as opposed to 4, 6, and 8, where it is less steep. And we said the steeper the graph, the faster the reaction. Therefore, your answer is going to be A, 1 minute. And the student repeats the experiment with the same volume and the same concentration of acid, but with 15 grams of smaller marble chips. And on the grid, we want to sketch a curve to show how the experiment would show on the curve. So let's just go back and check. Well, we already had 15 grams, but we had large marble chips. So what we're doing is we are decreasing our particle size. We know that decreasing the particle size is going to increase the rate, because we're getting that larger surface area. So that should then give us a steeper curve. What's important to know though is that because we are using 15 grams again, our curve should level off at the same place. So we shouldn't be making any more than this amount. So I know it's slightly hidden, but I'm going to draw a rough graph to show it should be steeper and then leveling off at the same height as the original curve. So then we can see our answers to our questions, where we said that what was going to happen to the mass? Well, the mass was going to decrease because of the carbon dioxide leaving. Why did the reaction stop? Well, we used up all our hydrochloric acid. And how did we know this? It was because our mass stopped decreasing. We said that the graph was going to be the fastest at A, 1 minute. And we said that we also had to draw our curve steeper, but making sure it levels off at the same height. That is a 7-mark question, and you can easily pick up 7 marks just by following the key rules and explanations that we went through in this video. I hope this has been useful for you, and if you have any questions, please feel free to leave a comment underneath, and I hope to see you back on the channel in the future to have a look at what other videos we have.